In this video, I will show you how to solve Prelab questions 1 and 2 using Microsoft Excel. Question 1 asks you to calculate the equilibrium constant for equilibrium system involving cobalt chloride in water. It gives you a table of 10 samples with the light absorbance at 710 and 740 nanometer. This table is a mimic of the result you are going to get in the experiment. Here is what you are going to do in the lab. You are going to have 10 test tubes. Into each of the test tube, you will add 1 milliliter of cobalt chloride with 1 molarity concentration together with different volume of water and hydrochloric acid. The cobalt ion from cobalt chloride either combines with water to form a pink-colored octahedral cobalt hexahydrate, or it combines with chloride to form a blue-colored tetrahedral complex. The conversion between these two complexes is shown in this reaction equation, and the equilibrium constant of this reaction is going to be calculated. As we discussed in the recitation class, these two complexes absorb light at different wavelengths. The hexahydrate compound absorbs light weakly, while the tetrahedral complex absorb light strongly, particularly at 710 and 740 nanometers. And therefore, the absorbance at these two wavelengths can be attributed to the cobalt tetrachloride complex only. In other words, we can use this absorbance to calculate the cobalt tetrachloride complex concentration. So let's add a column here to calculate the concentration of cobalt tetrachloride. We are going to use Beer's law. Now the law says the absorbance is equal to the concentration times extension coefficient and the length of the cuvette, which is usually 1 centimeter. The concentration is therefore equal to the absorbance divided by extension coefficient and the length of cuvette. Now, to use this equation, you have to know the extension coefficient, which we can calculate by absorbance divided by the length of the cuvette and the concentration. And therefore, to calculate the extension coefficient, we need a solution of known concentration. Now let's look at this table again. In number 1 test tube, 0 hydrochloric acid is added. The solution is essentially 100% cobalt hexahydrate complex. Now pay attention to the color of this number 1 test tube in the experiment. Is it pink? Number 10 test tube, however, contains the highest hydrochloric acid, which means the solution is essentially entirely cobalt tetrachloride ion. Now pay attention to the color again in the experiment. Is number 10 test tube blue? In other words, the concentration of cobalt tetrachloride ion in number 10 test tube should equal to the total concentration of cobalt ion, or the cobalt chloride concentration that you added in the system. What is it? It should equal to 1 milliliter, which equals 0.001 liter, multiplied by 1 molarity, and that gives you number of moles of cobalt chloride added in the system, divided by the volume of the test tube, which is 1 plus 9, and that is 10 milliliter, times 0.001 converted to liter, and that gives you 0.1 molarity. This is the concentration of cobalt tetrachloride in the test 10 tube. With this in mind, we now calculate the extension coefficient. The absorbance at 710 and 740 are both due to the cobalt tetrachloride complex ion. So which one should we use to calculate the concentration? It turns out that any absorbance value 2.0 and above are too strong and off scale for the spectrophotometer. They are not reliable. Therefore, for these test tubes from 7 to 10, we need to use the absorption values at 740 nanometers. Now, type epsilon 740 to represent the extension coefficient at 740. To calculate, we need to type equal, and using this equation, which says the absorption, we choose number 10, absorbance at number 10. We choose this number 10 because we know the concentration is 0.1. So divide by 1 centimeter, divide by 0.1, enter. And that gives you the extension coefficient at wavelength 7.740 nanometer. Using this value, we can calculate the concentration for test tube 7 to 10. For example, in number 7, we type equal, and we use this equation, which says the absorbance, okay, in this case, equals absorbance here, absorbance divided by extension coefficient 10.86 divided by 1 centimeter. All right, and that's the concentration for test tube 7, and then copy this equation and paste into the other cells. Not surprisingly, you see you get concentration 0.1 for test tube number 10. Now, what about test tube number 1 to 6? You can see that the absorbance at 710 are much stronger than those values from 740. Okay, because they are stronger, they are larger, so these values are more reliable than 740. And therefore, we will calculate concentration flow for test number 1 to 6 using 710 values. So first, we need to calculate extension coefficient at 710. So type extension coefficient 710. All right, now we notice that in the same test tube, same concentration, the absorbance ratio at 710 to 740 should equal to the ratio of epsilon of 710 to 740. That leads to this equation, and that is the epsilon at 710 can be calculated using epsilon 740. This is the ratio of absorbance of a particular test tube. Now we choose test tube 6, and because the value at test tube 6 is the largest, and therefore is the most reliable. So let's calculate. So here, let's type equal, and using this equation, and type epsilon 740, which is 10.86, multiply by absorption at 710. So 710 for tube 6 is 0.593 divided by absorbance at 740 for test tube 6, this value, enter. Okay, so this is the absorbance extension coefficient at 710. Using this value, we'll calculate the concentration from test tube number 1 to 6. For example, let's calculate number 1. So using this equation, so this should equal to the absorbance at should equal to absorbance at 710. Okay, divided by extension coefficient, we use this one, so 303 6.67 divided by the 1 centimeter. Okay, again we copy this equation, paste to other cells. Okay, that complete the calculation of concentration of cobalt tetrachloride complex ions. To calculate the concentration of cobalt hexahydrate, we use the total concentration of cobalt, which is 0.1 minus the concentration of cobalt tetrachloride complex. Copy paste. Now calculate chloride concentration in the solution. We are going to use this equation. In the first term is the chloride ion coming from hydrochloric acid. If you look at this table, we add different volumes of hydrochloric acid, 12 molarity. So the volume times 12 give you the number of moles, millimoles, divided by the total volume in each tube, which is 10 milliliter. You can see 1 plus 9 is 10, 1 plus 8 plus 1 is 10, 1 plus 7 plus 2, they are all 10 milliliters. Okay, so the second one is the chloride ion coming from cobalt chloride. The concentration of cobalt chloride is 0.1, and each cobalt chloride contains 2 chlorine, so it's 0.2 molarity. And now some of this chloride will form a cobalt tetrachloride, and so you minus the chlorides that form cobalt tetrachloride. You times 4 because each ion contains 4 chlorides. And this calculation gives you the concentration of free chlorides in the solution. And so let's calculate equals to the volume of hydrogen chloride. So we need another cell. We need another column, which is 12 milliliters. So here, millimeter, 12 molarity of hydrogen chloride, and 0 and 1, and can just go, and that give you the volume of hydrogen chloride in the solution. And now, according to the equation, which equals to volume of HCl times 12 divided by 10 plus 0.2 minus 4 times cobalt tetrachloride, and copy paste. So now we have the concentration for all the ions. We can calculate the equilibrium constant, okay, which equals to according to this equation is the cobalt chloride, so cobalt tetrachloride divided by cobalt hexahydrate and divided by chloride raised to the 4th power, and copy paste. Note that the last tube, the K constant cannot be calculated because we divided by 0, and this is because in the number 10 the chloride exists exclusively as cobalt tetrachloride. There's almost 0 cobalt hexahydrate. And whenever you calculate K concentration, if one concentration is too small, the calculation is not reliable. For the same reason, we shouldn't include number one test tube. So we are going to calculate average with using these values. Okay, so now average A, which equals average these values. Okay, that's the average K constant. Now let's solve the question number 2. Use Excel to plot percent distribution of cobalt hexahydrate and cobalt chloride as function of initial hydrochloric acid from the data in question number 1. So first you need to copy some of the data from question number 1. So this is the volume of hydrochloride you add it into each test tube. To calculate initial hydrogen chloride acid concentration, here let's add a column, and the concentration is calculated by the volume times molarity, which is 10 divided by 12 divided by 10. That's the volume of the solution in each tube. Okay, and copy paste. So this is the initial hydrochloric acid concentration. To calculate the percent of these two complex ions, we have add two columns. All right, let's copy. And the same thing is here. All right, so to calculate percent of cobalt tetrachloride, we use the concentration of cobalt tetrachloride divided by the total concentration of cobalt times 100. Copy paste. All right, the percent of cobalt hexahydrate is equal to the concentration of cobalt hexahydrate divided by 0.1 times 100. And copy paste. So now let's select this data. So this column will be x-axis and these two are the y-axis. This will be the series 1 cobalt tetrachloride and this one cobalt hydrate will be the series 2. So let's insert chart. Oh, no. Here, let's use smooth, scatter with smooth, and make this look better. We are going to choose data. Series 1 is the cobalt tetrachloride. And number 2, CO2 is the cobalt hexahydrate. All right, go here. All right, the range of this make a little bit change. So the range, let's put the minimum -10, and that would look a little better. And let's add axis titles. Okay, so y-axis is the percent distribution. The x-axis will be the initial hydrochloric acid. And let's go here. The title is let's just copy here. The percent of distribution of these ions as function of HCl. All right, so you can play around and make it look better. And I suggest that you use Microsoft Word to write your report, introduction, observations, setup, procedures, and copy this data from this Excel and paste onto the Word file and write your conclusions. All right. Good luck. Bye.